Starting with first question of control system, which was asked in SET1, and this question was of 1 marks. In this question, the 3 statements are given. There are 2 sets of a statement, and in the first set, 3 statements are given about stability of a system. And here we have 3 statements about the first column of Routh-Hurwitz table. So in Routh-Hurwitz table, we know that if in the first column all the coefficients are positive, or if all the coefficients are negative, or we can say that if there is no change in sign in the first column of Routh-Hurwitz table, the system will be stable. So the first statement is the system is stable. So in the second set, when all the elements are positive, if all the elements are positive or if all the elements are negative, then there will be no change in sign of first column. So x will be matched with p. The system is unstable. If there is a change in sign in the first column, the system will be unstable. When there is a change in sign of coefficient, so y will be matched to r, and the remaining statement is z, and here we have remaining statement as q. If there is a 0 in the first column of the Routh-Hurwitz table, then the test will break. Okay. So this will be the answer. This question is about finding stability with the help of Nyquist plot. So in Nyquist plot, how do we find stability? We write this formula: n is equal to p minus z, where n is equal to, what is n? N is number of anti-clockwise encirclement of -1 plus j0, number of anti-clockwise encirclement of -1 plus j0 in complex plane of open loop system, open loop transfer function. So you have GSHS. So in GSHS, what we do, in S plane we move from 0 to infinity on j omega axis, and the corresponding plot we get in GSHS plane is called polar plot. Then we move from making infinite radius, we move from 0 plus to infinity, then making radius of plus infinity, we move from plus infinity to minus infinity, and then we again go back to 0, then making a radius tending to 0, we again reach from 0 minus to 0 plus. So this way we cover entire right half of S plane, and in entire right half of S plane, if there is a 0 or if there is a pole, the effect of pole and 0 will be reflected in the complex plane of open loop transfer function. So this way we move in S plane and we try to find out n, the number of anti-clockwise encirclement of point -1 plus j0. Let's say this is complex plane of GSHS. This is imaginary part of GSHS, and this is real part of GSHS. And here we have -1 plus j0. So this is n is anti-clockwise rotation. What is p? P is right half pole, because we cover right half of S plane only. This is S plane. We cover entire right half of S plane. So here P and Z will be right half poles and zeros of S plane. Right half pole of GSHS, and this is also equal to right half pole of 1 plus GSHS. In the theory lecture I have proved that P is right half pole of GSHS and this will be equal to right half pole of 1 plus GSHS. But we are interested to, in lecture I have focused that many times I have mentioned that we are interested in finding out the right half zeros of 1 plus GSHS. We are interested in finding out right half zeros of 1 plus GSHS because right half zeros of 1 plus GSHS makes the pole of closed loop transfer function. Z is nothing but number of right half poles of closed loop transfer function, because this term, the zero of this term appears in the closed loop transfer function. This term appears in denominator, so the zeros of this term will be pole of closed loop transfer function. Okay, so this is the formula to find out stability with the help of Nyquist plot. So coming to option A, encirclement of a closed loop control system is stable if the Nyquist plot of corresponding open loop transfer function, okay, the Nyquist plot is of open loop transfer function, encircle the S plane point -1 plus J0 in counterclockwise direction as many times as the number of right half S plane. So for stability, what should be the value of Z? The number of zeros, the number of right half zeros of 1 plus GSHS must be 0. There must not be even a single 0 of 1 plus GSHS which lies in the right half of S plane. So we will have to put Z equal to 0. So this way we will get the number of anti-clockwise encirclement must be equal to number of right half pole. So the number of the encircles the S plane point -1 plus J0 in counterclockwise direction as many times as the number of right half S plane pole. So this option looks correct. In the second option, the point is given as 0 minus J1. This option talks about this point, so we are not interested in this point. This option will be wrong. In C option it says encircle the S plane point -1 plus J0 in counterclockwise direction. Up to here a statement looks good, as many times as the number of left half S plane pole. Here this option says about left half S plane poles. We are not interested in left half S plane pole because while making Nyquist plot we cover entire right half of S plane. In the D option, encircles the S plane point -1 plus J0 in the counterclockwise direction as many times as the number of right half S plane zeros. So it talks about S plane zeros, but for stability n should be equal to right half S plane pole. So this option is also wrong. So A will be the correct option. In this question, we are given with a open loop transfer function, OLTF for open loop transfer function. We are given with open loop transfer function of a unity feedback control system, and we have to find out the value of K when the breakaway occurs. The value of K at the breakaway point of the feedback control system's root locus plot is. On the root locus plot of the closed loop system, there will be a breakaway point. So we have to find out the value of K at that breakaway point. So to find out breakaway point, what we do? We write this equation 1 plus KGSHS. This will give you the equation for, this will give you the characteristic equation of closed loop system, and on the root locus 1 plus k GSHS will be 0, and GSHS is nothing but, in this equation GSHS is given as 1 upon s square plus 5s plus 5. Okay, so 1 plus k divided by s square plus 5s plus 5 equal to 0. To find out the breakaway point, what we do? We do dk by ds equal to 0. So this way we will find out the value of s at the breakaway. Then what we will do? We have the value of s and we will have relationship between k and s. So using that value of s, we can find out the value of k, but we have to check that, we have to confirm that that value of s will be on root locus. In the lecture we have studied that you may get more than one value of s with the help of this equation, but all the values of s will not lie. It is not necessary that all those values of s will lie on the root locus. So before finding out the value of k, we need to first check that value, whether that value of s lies on root locus or not. So that k will be equal to minus of s square plus 5s plus 5. When you will do dk by ds, you will have dk by ds equal to minus of 2s plus 5 equal to 0. So s will be minus 2.5. So we are getting only one value. Okay, now we will check whether this point lies on root locus or not. So how do we check whether a point lies on root locus or not? If a point, we studied in theory that if a point lies on root locus, if a point S1 lies on root locus, then the angle of GSHS at that point, this will be equal to 180 degree or minus 180 degree. This is the condition of a point to lie on root locus. This we have already studied in lecture, and that video has already been uploaded on YouTube. So for detail you may refer that lecture. So what is GSHS? We have to find out angle of GSHS when s equal to minus 2.5. So this will be 1 upon s square, so minus 2.5 square plus 5 into minus 2.5 plus 5. This will be minus 6.25, no, plus 6.25 minus 12.5 plus 5. This is 1 upon 11.25 minus 12.5. So here you are going to get a negative quantity. So if GSHS, the value of GSHS at S1 is a negative quantity, in the complex plane of GSHS, here you have imaginary part of GSHS and here you have real part of GSHS. You have a real quantity which is negative. So you will be somewhere on the negative real axis. So at this point angle will be 180 degree or minus 180 degree. So it confirms that the point S is equal to minus 2.5 lies on root locus. Okay, so this point lies on root locus. Corresponding to this point, k will be equal to minus of s square plus 5s plus 5, minus 2.5 square plus 5 into minus 2.5 plus 5. This will give you, we will solve this, This will give you k equal to 1.25. There is another method to find out the breakaway point. Since this is a second order system, so in the root locus or in the closed loop system you will have only two roots. And what will be the closed loop transfer function, or what will be the characteristic equation? The characteristic equation will be given by 1 plus k GSHS. So 1 plus k divided by GSHS is s square plus 5s plus 5. S square plus 5s plus 5 plus k. So this will be your characteristic equation. This is characteristic equation. And to plot the root locus, we equate it to 0 and we find the values of s to make this equation 0. And location of all these values of s, we vary k, and by varying k, to equate this equation to 0, all the values of s will make the root locus. And what will happen at breakaway point? This is a second order equation, so you will have only two solutions. And we know that at breakaway point the two roots will be equal. In the root locus, suppose we have two poles moving like this, so at breakaway point both the poles meet. So at breakaway point the value of two poles will be same. Let's say this point is A. Okay. So if A is a solution of this equation will be divisible by s minus A, and the another solution is again A, so this must be divisible by s minus A again. So this equation will be divisible by s minus A whole square. This equation must be divisible by s minus A whole square. So we will divide it and the remainder must be 0. S minus A whole square is s square minus 2as plus a square. S square minus 2as plus a square, minus plus minus. Here you will have 5s plus 2as plus 5 plus k minus a square equal to 0. Okay. Now order of this equation is less than here order of equation is 2, so we will not divide any further. This is the remainder and this has to be 0. Here you have power of s as 1, so this has to be individually 0, and this is a constant, so this has to be individually 0. So 5 plus 2a must be equal to 0, and 5 plus k minus a square has to be 0. From here you will find a equal to minus 2.5. Okay, a is equal to minus 2.5, and if you will put a equal to minus 2.5, you will get k as 1.25. The answer to this question will be k equal to 1.25 for positive value of k. In this question we are given with open loop transfer function of a unity feedback control system. The open loop transfer function of a unity feedback control system is given as gs equal to k divided by s into s plus 2, and for a unit step input, the peak overshoot of the system has to be 10%. Then we have to find out the value of k. Okay, we have to find out the value of k such that the peak overshoot of this system for a unit step input has to be 10%. So first I will write the formula for percentage peak overshoot. This is equal to e to power minus pi zeta divided by root under 1 minus zeta square, where zeta is equal to damping ratio. Okay. And the general equation of a closed loop, a second order system is s square plus 2 zeta omega ns plus omega n square. We have open loop transfer function. So if I make the block diagram of the closed loop system, unity feedback closed loop system, then we will have k divided by s into s plus 2. Here we have negative unity feedback, and this is unit step input. What will be the closed loop transfer function? The closed loop transfer function will be k divided by s into s plus 2 divided by 1 plus s into s plus 2. Closed loop transfer function will be k divided by s square plus 2s plus k. This is the closed loop second order system. Okay. So by comparing, we will first find out the damping ratio in terms of k. Now we will put that, and from this equation we will find out the required damping ratio, and here we will have the damping ratio in terms of k. So that way we will find out the value of k. So percentage damping ratio is this has to be 10%. To calculate in percent, we have to multiply it by 100. So this is 10%. So 10% must be equal to e to power minus pi zeta divided by root under 1 minus zeta square into 100. So pi zeta divided by root under 1 minus zeta square equal to ln 10. Okay, here we will get zeta square divided by 1 minus zeta square equal to 0.5377. This is required equation for zeta. And now if we compare, for this system we will try to find out the value of zeta in terms of k. So if you compare, we have omega n square equal to k, so omega n equal to root under k, and here 2 zeta omega n is equal to 2, so 2 zeta omega n equal to 2, so zeta equal to 1 upon omega n, that is 1 upon root k. So zeta square will be 1 upon k. Here zeta square will be 1 upon k divided by 1 minus 1 upon k. This is equal to 0.5377. Okay. So this way we will get k equal to 2.8596. In this question we are given with a transfer function of a linear time invariant system, and we have to find out the number of zeros in the right half of S plane. So to find out the number of zeros of this equation, or to find out the number of solutions of any equation which lies in the right half of S plane, that means the positive values of it, the positive solution of S, this equation, not positive value. Okay, we have to find out number of zeros in the right half of S plane. So in Raoult-Hurwitz, what we do, we check the stability of a system by checking the number of right half poles of a system. Let's say the equation is k divided by 2s4 minus 5s cube plus 5s minus 2. Let's say this is a closed loop transfer function of a system. So how do we check the stability of this system? We make Raoult-Hurwitz table for this characteristic equation. So the same characteristic equation is given here. And what we do, we form the Routh-Hurwitz table and we check the number of change in sign in the first column, and we say that the number of right half pole of this closed loop transfer function will be same as the number of change in sign in the first column of Routh-Hurwitz table. So to form the Routh-Hurwitz table, so the number of right half pole of this closed loop transfer function will be same as the number of right half solution of this characteristic equation, or the number of right half zeros of this equation. We have S4 s square s to power 0, s cube s square s to power 1, and s to power 0. Here we will have 2 s to power s. There is no term of s square, so we will have 0 here. Here we have minus 2. In the second row we will have power of s cube minus 5. There is one sign change, and power of s, that is plus 5. This is s4 s cube s square s to power 1 and s to power 0. Now here what we will have, this is calculated as b minus at by c, or bc minus at by c. So to find out this element, for this element this will be a, this is b, this is c, and this is d, and we have to find out b minus at by c. 0 minus 10 divided by minus 5, 0 minus 2 into 5 divided by minus 5, this will give you 2. To find out this element, a and c will be same, and this will be b, and here we have 0, this will be d. This will be b minus ad by c. Since d is 0, so ad will be 0. Here you will have minus 2, and here 0. Now to find this, this will be a, b, c, and d. So b minus ad by c, 5 minus 10 divided by 2, this will give you 0, and here again you will get 0. So if complete row is 0, this is surely an unstable system, because there is a one sign change. So this is an unstable system, and to further complete the Routh-Hurwitz table, if one complete row is 0, what we do, we first form the characteristic equation of using the row which is above this 0 row. So what will be characteristic equation here? We will have 2s square, and this is, here you have s square, this will be s to power 0. 2s square minus 2 equal to 0. If complete row is 0 and you have to completely form the Routh-Hurwitz table, what we will do, you will use the elements of row above the 0 row to form the characteristic equation. So here the characteristic equation will be 2s square minus 2 into s to power 0. And now you differentiate it. If you will differentiate it, you will get 4s. Okay, so the coefficient of s will be 4. Here we will write 4, and this will be 0. Okay, to find this element, this will be a, this will be b, this is c, and this is d. Since d is 0, so ad will give you 0, so we will have here minus 2 only, and here 0. Now we will check the first column of Routh-Hurwitz table. Okay. So here plus to minus one sign change, here we have minus to plus second sign change, and here is no sign change, but after 4 to minus 2 there is again one sign change. So we have 3 sign change. Okay, so it means this equation has 3 zeros which lie in right half of S plane.